Hello everybody. In this video let us know about entropy. So entropy is a Greek expression used for transformation concept. Right? Now if we take isothermal process, temperature remains constant, right? Temperature remains constant. If we take adiabatic process, no heat is added to the system or no heat is removed from the system. Means in adiabatic process temperature changes. Okay, neither heat nor temperature is constant, both will change. Okay, so now here if we take the adiabatic process, when gas is compressed adiabatically, if we see when gas is compressed adiabatically, okay, when gas is compressed adiabatically, what happens here? Heat energy, compression means additional heat will be formed, heat of compression will be formed. So heat energy increases means temperature increases. On other hand, if gas is expanded adiabatically, heat energy decreases, temperature decreases. So totally there will be temperature changes. Even though the process is taken under perfect isolated conditions, means no heat transfer from system to surroundings. Only I said no heat is added, no heat is removed. Means no heat transfer from system to surroundings. The process takes place under perfect isolated conditions. So here, but if we take gas compressed adiabatically, temperature increases, expanded adiabatically, temperature decreases. Means temperature changes takes place. So Clausius said that as temperature remains constant in isothermal process, some physical quantity remains constant in adiabatic process. So some physical quantity remains constant in adiabatic process. So that physical quantity which remains constant in adiabatic process, we call it as entropy. The physical quantity which remains constant in adiabatic process, as if temperature in isothermal process, we call it as entropy. Actually there is no perfect definition for entropy, just we will talk the concept of entropy itself only. Alright. Now such entropy is denoted by letter S and is written as heat energy divided by absolute temperature. We call it as change in entropy. We talk in terms of change in entropy only. So dq by t, we write it as ds. This is the mathematical form of entropy. Okay, the mathematical form dq by dt equal to ds, mathematical form of entropy. Now dq, we can write it as tds. This we call it as mathematical form of second law of thermodynamics. What is the mathematical form of second law of thermodynamics? dq equal to tds. Right? Now next, let us go for physical significance of entropy. Okay. So now what we said, change in entropy is equal to change in heat by temperature. Okay. Now here the entropy means, so in mechanics we saw that mass means it bears to linear motion in mechanics. Okay. Similarly, moment of inertia bears to rotational motion. Rotational motion. So in similar way, entropy bears to heat motion. Entropy bears to heat motion. Okay. Now next, entropy is termed as thermal inertia. A bit, entropy is termed as thermal inertia. Okay. Now next, the increase in entropy. Increase in entropy means nothing but transition of thermal energy. Transition of thermal energy from more available to less available form of energy, less available form of heat. Means here more heat is converting into work, we can say. Right? Now next, entropy can also be said as the measurement of randomness. Okay, or randomness means disorder of molecules. Randomness or disorder of molecules. So increase in entropy means, here in case of randomness or disorder of molecules, increase in entropy means nothing but moving from ordered state to disordered state. Ordered state to disordered state. Right? Now next, if we take Carnot reversible cycle, for reversible process or reversible cycles, entropy remains constant. This is also a bit. Entropy remains constant for reversible process. For irreversible process, entropy increases. Okay, for irreversible process, entropy increases. Okay, that is, it will be positive. Okay. Now next, we can also take as a PV diagram temperature entropy diagram we can draw. How we draw the PV diagram for Carnot cycle? The same Carnot cycle I am taking, but on temperature entropy diagram. So isothermal process, temperature remains, so entropy formula ds is equal to dq by dt. Temperature remains constant here, right? Okay. Now adiabatic process or adiabatic expansion, here temperature changes. Now next, isothermal compression, again temperature remains constant. Adiabatic compression. By considering all this, again we can find efficiency as 1 minus T2 by T1. And the uses of entropy is we use in meteorology. Okay. So we use in predicting the defects in performance of engine. We can check the efficiency of engine. We can obtain the work value of fuel. The uses of entropy or TS diagram is it is used in metrology, predicting the defects in performance of engine, check the efficiency of engine, and next it checks the work value of fuel, right? Now next, now we said that ds is equal to dq by dt, right? Or dq is equal to tds, put equation 1, right? Now next, if 1 mole of gas is heated at a constant volume, then what we will write? dq as cv dt. At constant pressure, what we will write? dq equal to cp dt. Now let us do equation 2 divided by 1. 2 is cv dt by 1 is t ds, and dq strikes off, dq by dq. So cv by t dt by ds is equal to 1, or dt by ds is equal to t by cv. Similarly, if we do equation 3 divided by equation 1, we get dt by ds is equal to ct by cp. As cp is greater than cv, we know that cp is greater than cv, we write this, we call it as slope of isochoric curve. What is this? Slope of isochoric curve. This what we will call? Slope of isobaric curve. Slope of isobaric curve. Now next, now as cp is greater than cv, we write slope of isochoric curve divided by slope of isobaric curve is equal to t by cv by t by cp, that is equal to cp by cv, which is equal to gamma, right? Now next, entropy of perfect gas. Entropy of perfect gas. Now here 3 relations we will get. The first relation is this all changes in terms of pressure, volume, temperature only. We are writing the expressions. Now first we are keeping pressure constant. Then the change in entropy, final entropy, initial entropy, is equal to Cv log E Tf by Ti plus R log E Vf by Vi. Now next, if volume remains constant, change in entropy is written as Cp log E Tf by Ti minus R log E Pf by Pi, right? Similarly, when temperature is kept constant out of these three terms, the change in entropy, it is written as Cv log E Pf by Pi plus Cp log E Vf by Vi, right, for perfect gas equations. Now next, change in entropy when ice changes to steam. Okay, it is written as M L1 by T1 plus 2.3026 MC log base 10 T2 by T1 plus M L2 by T2. Now this is when ice starts melting. Okay, so L1 latent heat of fusion we will take, right? Now this, when ice converts into water and starts boiling, means until boiling point only. Now this is ice started converting into boiling, that is, it is converting into vapors, that is steam we will call. So L2 we call latent heat of vaporization, right? First it converts into water, melts, then starts heating, then converts into vapors or steam, right? Now next, change of entropy, change of entropy in heating substance. What will be the formula? If we take any liquid which is supposed to be heated, 2.3026 MC log 10 T2 by T1, the same one we wrote, right? Now change of entropy during free expansion, change of entropy during free expansion, we will write it as delta S is equal to mu R log E Vf by Vi, right? Now next, if we take some more entropy changes, some few, I am writing. First, before going for that, dimensions of entropy are, dimensions of entropy are energy and temperature only. Okay, so it is quoted in joules per degree Kelvin per mole. Okay. Now next, entropy is variable state, depends only on initial and final states of system, not on path. Okay. Now next, if we take entropy changes, isothermal expansion of ideal gas into vacuum, then what will be the formula for entropy change? What happens? Entropy will be greater than Q irreversible process, the heat in irreversible process, divided by absolute temperature. At constant volume and constant pressure, the change in entropy is written as integration T1 to T2 CV differentiation of log T for constant volume. For constant pressure, same T1 to T2 Cp differentiation of log T. Right? Now in terms of phase change, the change in entropy is written as heat content delta H phase change divided by temperature. Now variation in Cp with temperature. Right. So if heat capacity of system is given as function of temperature, then C is written as A plus Bt plus Ct square, so on, plus so on. So by considering this, the change in entropy is written as A log T2 by T1 plus B T2 minus T1 plus C by 2 T2 square minus T1 square plus so on. Right? So these are some basics are related to the entropy. And now once let us go for Clausius Clapeyron latent heat equation. Most important. So dP by dt equal to L by T V2 minus V1, latent heat, T temperature. So the effect of, if we talk about pressures, if V2 is greater than V1, dP by dt is positive. So effect of change of pressure on melting point we are talking. So here melting point increases with increase in pressure. If V2 is less than V1, dP by dt is negative. So melting point decreases with increase in pressure. Right? Similarly, let us talk about effect of change of pressure on boiling point. If V2 is greater than V1, dP by dt is equal to positive. So boiling point of substance, boiling point increases as pressure increases, boiling point decreases as pressure decreases. Okay. Now next, entropy of mixing of ideal gas, if we take more than one ideal gas, then what will be the change in entropy? It is written as delta S is equal to Rn1 log P1 naught by P1 plus N2 log P2 naught by P2. Okay, where R you all know as it as gas constant. N1, it is mole of first gas. Two gases we took, you think? No. P1 naught, initial pressure of first gas. Now next, N2, mole of second gas or another gas. P2 naught, initial pressure of that second gas. And P1, P2 in the formula we call partial pressures of the first and second gases. P1 is written as x1 Pt, P2 is written as x2 Pt, where x1, x2 are mole fraction of two gases, right? Now Pt is total pressure of mixture of gas. Okay, in some special cases, right, we take Pt equivalent to P1 naught, that is equal to P2 naught. Okay, so in such cases delta S is equal to minus R, substituting in above equation N1 log x1 plus N2 log x2. The different kind of expressions useful for mathematical forms or doing problems. Now second problems will be asked in the exam on second latent heat equation. Remember it. So in my last video I did one problem on this. dl by dt equal to L by T plus C2 minus C1. L by T plus C2 minus C1. Okay. So thank you for watching my video. If you like it, share it, subscribe it. Thank you.